All right, for the Unit 3, Lesson 2, Go, from the Ready, Set, Go problem set, I'm just going to go over questions 11, 12, 13, and 15. There's two 13s. Well, that's a mistake. This 13 at the bottom left and the 15. So I guess that's really probably questions 15 and 16, but all right, so, oh, it's so funny just finding some little typos that we thought we caught and maybe not. So, all right, so write equations for the given tables in both recursive and explicit form. So before I can do either of those things, I need to observe how the function is changing as n increases by 1. And in my first table, that's not going to be too bad because the n values are increasing by 1. So I know right now I'm looking for either an addition or multiplication pattern, and I'm going to check addition first. So from 5 to 2, I would be decreasing by 3, and then 2 minus 3 is also -1. So I know that this is a linear function because I'm observing an arithmetic sequence because I see that I'm adding -3 or subtracting 3 each time. So I know that in a linear function, that turns into my slope, my change in y over my change in x. And -3 over 1 is just the whole number -3. So when I'm writing my explicit equation, I could start at this first ordered pair and I could say f of n equals, well, I'm going to start with the number 5 and then I'm going to subtract 3, but I'm going to subtract 3 n minus 1 times. So if I think about it, this is like 5 minus 3 0 times, 5 minus 3 1 time, 5 minus 3 2 times because I had to subtract 3 twice to get to -1. And again, I could observe that this number is always 1 less than n. I could also just think of this as being point slope form that we learned about in our last unit. And this would be the same as saying f of n equals -3, my slope, n minus 1, since I'm starting at my first value, plus 5. I could have also chosen, I'm not going to do this for all of these, but just to review, I could have used the point at 2 and had a plus 2 right here, or I could have used my point at, sorry for the dog in the background, at n equals 3 and had a -1 here. So these are all different versions of the same equation in point slope form, or you might have gone back and found the y-intercept. If I worked backwards and added a 3 to that, I could say f of n is -3n plus 8, or 8 minus 3n. All right, so there's a bunch of explicit equations. You only need one, but I thought this was a reteachable moment. All right, for the recursive, that's where I'm going to describe what I'm doing to my previous term to get to my next term. So to get to my term f of n, I'm going to take my previous term, that's where n is less 1 than my current term, and I'm going to subtract 3 from it. And remember, my recursive equation isn't complete until I have given a value, like a starting point. So f of 1 equals 5. All right, let's look at number 12. All right, so again, I want to look at the pattern. This table starts off easy because n is increasing by 1. And at first, I might say, oh, I'm adding 6. But 12 plus 6 is 18, not 24. So that means I need to consider a different pattern. Maybe I'm multiplying by 2. That pattern works. So if I'm multiplying by 2, I know this table represents an exponential relationship, or I could think of this as being a geometric sequence because I have multiplication. And so for an exponential, I could use this form of y equals my y-intercept times my growth factor to the power of x. Or I could just think of it this way. Well, let's look at it two different ways, actually. So I don't have my y-intercept in this table, But just like we did with point slope form, if this is some other y value that's not my y-intercept, this would be that corresponding, this would be my corresponding x value. So I could do this similar to point slope form. The way we have done this more authentically in our unit 1 is I said, like, if this is 6 times 2 0 times, this is 6 times 2 to the first power. This is 6 times 2 to the second power. Because remember, back in unit 1, we would have listed this as like 6 times 2 times 2. We would have generalized that with an exponent. Again, I could observe that every time I do that, this number right here is 1 less than n. So in unit 1, I would have written this explicit equation as like y equals, I would start with my number 6, 2 is my growth factor, my multiplier, and I could have said x minus 1. We don't call this point slope form because it's exponential and I don't have a slope, but it's otherwise a very similar idea. Had I started with 12, I would have a 2 here in x minus 2. Or had I started with the 24, the y value 24, my growth factor is still 2, but I'd have x minus 3. So all three of those work. If I want to go back to how I usually write an exponential, if I find my y-intercept when n is 0, I'm so sorry, I can't get this dog to stop playing with this toy. If I go back and divide by 2, I would have a 3 there. So I could also write this as 3 times 2 to the power of x. So those are 4 different possibilities. They're all correct. They're all explicit equations that work. All right, for the recursive, again, if I want to get to some term f of n, I'm going to take my previous term, which is where n was 1 less than my current term, and I'm going to multiply that by 2. And so you could also write that as just 2 times f of n minus 1. And again, our recursive is not complete unless we give a value from our table. So f of 1 equals 6. All right, I'm going to skip down to the second number 13, the bottom problem. And here I got to watch out because in my table, n isn't always changing by 1, but it is changing by 1 right here. So I want to think, do I likely have an addition or a multiplication pattern? And it seems most probable that I have an addition pattern of plus 2. So a way we could check to make sure that we're correct, this isn't too bad if our table's not too far away, if the numbers aren't spaced too far away. Shh, Nora. Sorry. Down, Nora. Let's see if she listens. I don't have a dog. This is someone else's dog. All right, so I'm going to make sure that this pattern of counting by 2s works. So if I go backwards, 11 minus 2 is 9, 9 minus 2 is 7, 7 minus 2 is 5. Beautiful. If I subtract 2 one more time, I have my y-intercept. So for the explicit equation, if I use, and again, this will be linear because we are adding, so we have an arithmetic sequence, a linear function. If I use my y-intercept, I could write this in the form of like 2n plus 3 because my y-intercept is the 3, and this would be like saying y equals mx plus b. But if I used another point in the table, I could use point slope form. So like 2 times n minus 1 plus 5, or 2 times n minus 4 plus 11, or 2 times n minus 5 plus 13. Any of those work. And remember, point slope form is where I have my slope. This is an x value, and this is the corresponding y value. So like 5, 13, my slope is 2 for all of those. All right, for the recursive, to get to some other term, I take my previous term, and I add 2 to it. Now my recursive isn't complete unless I give a value from my table, a known value. All right, let's go to the question labeled 15, although it's really 16 since we had 2 number 13s. Going back to n is constantly counting by ones. So n is increasing by 1 here. The question is, am I multiplying or am I adding? Well, let's see. Negative 4 times positive 4 is 16, or sorry, negative 16. And negative 16 times positive 4 is negative 64. So we have our y-intercept, which means we could use this form of our exponential since this is a multiplication pattern. So I could say f of n equals my y-intercept times my growth factor to the power of n. If I started at a different y value, let's say that I started with negative 16, my growth factor is still 4, but like we see in point slope form, I would subtract up there. So a couple ways we could write those. For my recursive formula, I'm going to multiply my previous term times 4. And again, I'm going to give a value from my table.